All right, so today we're going to finish up most of the material that I wanted to get to. I never expected to get to fluids, so we're just going to finish up. We're going to do our best to get through the end of chapter 6, and we're going to skip some stuff at the very end because while it's interesting, I just don't have time for it. But it might turn out, I only have 9 pages of notes here, so it might turn out that we end a little bit early, and that'll be, as a reward for sticking with me this whole time. So we finished off last time on Monday talking about 4 classes of special thermodynamic processes. These were isothermal, isochoric, isobaric, and adiabatic processes. Now we're going to see some more special thermodynamic processes in this. Oh, and we also talked about cycles. But now we're going to slap together these 4 special processes to make some real world useful cycles. So the first cycle to talk about is the Otto cycle. OTTO, named after a fellow whose last name was Otto. It turns out that this is also, or this is the cycle that used to be used in internal combustion engines inside cars. Modern cars use more efficient cycles, but they're just variations of the same theme. Now, it's just a coincidence that Otto and Auto, A-U-T-O, sound very, very similar. It's not the reason why automobiles are called automobiles. It's just a coincidence. So the Otto cycle is a very particular type of thermodynamic cycle. So we know that we can depict thermodynamic cycles by drawing a PV diagram for them. So I'm going to do that. So this is an engine. Come on. So we know that it's going to produce, you're going to input heat and it's going to produce work. So you start, say, down here. Let me do something really quick. Right, so let's say we start at point A. So this is an internal combustion engine. So the first thing that happens is, this would be what's known as a, well, I don't know if it would be a 2-stroke engine now that I think about it. So the first thing that happens is you have air flowing into the air and gasoline vapor flowing into your piston chamber. And then the piston compresses it very quickly. Now, we already know what happens, or we already know how we can approximate quick changes in volume. If the volume changes sufficiently quickly, then we can approximate that as an adiabatic process because there's just no time for the heat to go in or out of the system. So here we have an amount of gas mixed with gasoline vapor. So it's air mixed with gasoline. And then the piston compresses it very quickly. So that decreases the volume. Oh, this is volume. This is pressure in an adiabatic way. Up to a certain point. Call it, actually, let's do this a little bit better. There we go. Call that point B. Call this V min and V max. And it'll be clear why these are useful later. Then the gasoline air mixture is ignited. And so when that happens, the reaction takes place very, very quickly. So quickly, in fact, that the air gasoline mixture increases its temperature much, much faster than the gas could possibly push the piston and expand. So this would be an example of the volume staying fixed, but the temperature skyrocketing. And what would that do? That would increase the pressure. So this would result in a, so here we have an adiabat. So we can approximate that process as an isobaric process because an isochoric process, because the volume is staying roughly constant because it's happening so quickly. And yet the pressure is increasing. And that's just because it's heating up very quickly. Then you have a bunch of heated gas and there's a piston that it's pushing on. So it's going to push that piston up. Now it's going to push the piston very, very quickly because the pressure is so great. So this is going to happen sufficiently fast that that again, no heat can escape the system. So this is again going to be an adiabatic process. And then once it gets to its original volume, the now compressed gas, with the compressed gas fuel mixture that's been spent is expelled out the exhaust, and new air and new gasoline is added to the mixture. This results in the volume staying the same because the piston's in the same position. But now the high pressure gas is vented out and new low pressure gas is brought in. And this is another isochore. And this completes our cycle. This completes the Otto cycle. Now, clearly, this is just an approximation of a true internal combustion engine, but it's a fairly good one, right? Because this explains the cycle. And no, so a diesel engine and an Otto, the diesel cycle and the Otto cycle are different, even though they both use internal combustion. But anyway, so this is a fairly good representation of what happens. Now, we know that no heat goes in or out during adiabatic processes. So the only processes that can have heat flowing in or out are the two isochores. We know that heat is going to flow into the system during ignition, and heat is going to flow out of the system when the gas is exhausted. So, and let's call it QC, QH and QC. So in a real, sorry, that should be QH, not QC. In this engine, there actually is no hot reservoir, and there actually is no hot reservoir. Oops. Oh, where did it go? Okay, I guess it's here. Whatever. There is no hot reservoir, but there's something taking the place of the hot reservoir. Instead of having an actual hot area that you can use to very quickly heat up your gas, instead what's happening is we're using combustion. But that chemical process isn't a physical part of the gas. It's some external source of heat. And by external, I mean it's a result of some chemical thing, not some physical property of the gas. This is a difference between chemical processes and physical processes. So that's why it can be considered as external heat entering the system, even though it's technically internal to the system. I.e., you could precisely mimic this by, instead of burning gasoline, you just have something really hot that you put next to your piston to bring up its temperature very quickly. That would do the same thing as combusting the gasoline. Anyway, so we can ask then, so if we know what if we know the internal and, if we know the heat that flows in and the heat that flows out, we know that those take place during the isocores. We can use that to compute efficiency. Remember last time we talked about the efficiency of an engine? It is the effectively 1 minus the, or it's the work done divided by the heat that flows into the system, or equivalently, it is 1 minus the ratio of the heat that flows out of the system divided by the heat that flows in the system. So we can just compute this now because we understand isochoric processes. So we need to compute QH and QC. So QH, well, this is an isochoric process, which means that the volume doesn't change. So we can just use molar specific heat, or constant volume molar specific heat, to find that the heat that flows into the system is just the number of moles times the molar specific heat times the temperature difference, Tc minus Tb. Similarly, the heat that flows out also flows out during a constant volume process. So this would be NCV times Ta minus Tb. Oh, sorry, that should be Td minus Ta. If you wanted the correct sign instead of just the absolute value, you would do Ta minus Td, but we're just looking for absolute values here. And so we can compute the efficiency. The efficiency is 1 minus the absolute value of QC divided by the absolute value of QH, which is 1 minus NCV Td minus Ta divided by NCV Tc minus Tb. This simplifies down to 1 minus Td minus Ta divided by Tc minus Tb. Now, we could just say, okay, we're done. But this isn't a particularly useful formula because we would need to measure the temperature at all 4 points in our cycle, which is a little bit hard to do. So we can actually use more, and we can use what we learned. We can use more of what we learned to simplify this. So remember, for an adiabatic process, we know that T times V to the gamma minus 1 is constant. this can be derived using the P times V to the gamma is constant and the ideal gas law. So we can use that fact to write that TAVA, we have two adiabatic processes here. So T times V, that particular function of T and V should be equal at A should be equal to the same thing at B because there's an adiabatic process connecting them. So TAVA to the gamma minus 1 should be equal to TBVB to the gamma minus 1, and TCVC to the gamma minus 1 should be equal to TDVD to the gamma minus 1. That much is true. And now we're just going to define something that you may have heard of if you're into cars. We're going to define the compression ratio R, which is just the maximum volume divided by the minimum volume. This would be the volume at A or D, because they're at the same volume, divided by the volume at B or C. And so we can use the adiabatic relationship to find that TD is equal to TC times VC over VD to the gamma minus 1. That's just using this one. And then similarly, we can do the same thing for TA, but just as a quick further simplification, this is TC times R to the 1 minus gamma, because it's VD over VC would invert the exponent and make it negative. And then similarly, we have that TA is equal to TB times VB over VA to the gamma minus 1, which is just equal to TB to the R times R to the 1 minus gamma. And so the conclusion then, combining these two results, is that TD minus TA, which is something that we wanted to compute, that's the numerator here, this is equal to TC minus TB times R to the 1 minus gamma, right? And so the ratio of TD minus TA divided by TC minus TB, well, we can just solve for that here. Implies that TD minus TA divided by TC minus TB, that's just equal to R to the 1 minus gamma. And so we can plug that in. So the efficiency here is just 1 minus R to the 1 minus gamma. That is the efficiency of the Otto cycle. Now, like I mentioned before, the cycles that we're describing here are thermodynamic ideal cycles, meaning that they're quasi-static. And so the efficiency that we would get here is an upper bound on the actual efficiency that you will see in vehicles or in real-world engines. So for a typical value for an ideal Otto cycle, you might get that the efficiency here is 50%. Whereas for a real gasoline engine that uses some variant of the Otto cycle, you'll see maybe 35% efficiency. But the point is you could never expect that an engine with that particular compression ratio to exceed 50%, because that is the thermodynamic maximum for a given compression ratio. So you could find the thermodynamic maximum by finding R. And by the way, the point is the smaller R is, hold on, something's not right. I may have defined the compression ratio. Did I define the compression ratio backwards? No, that should be fine. Oh, yeah. So 1 minus gamma is negative. And so the larger R is, the more efficient your vehicle, or your cycle anyway. Because 1 minus gamma is negative. Because gamma is always greater than 1. Right, so that's the Otto cycle. That's a particular type of cycle. There's another kind that we could make, which is the diesel cycle, which is just a variation of the Otto cycle. Is this roughly how AC units work, by compressing Freon and letting it? I'm going to talk about that. But yeah, I mean, that's basically it. So the only difference between the diesel cycle and the Otto cycle is that instead of isochoric, ignition, which was the left process over here, it uses isobaric ignition. So it goes across instead. meaning constant pressure. So it lets, so the ignition is almost slower. And so the end result, and it just amounts to doing the same process again, but just for, in this case, the QH would be Cp rather than Cv. The end result is that the efficiency is 1 minus NCV Td minus Ta divided by NCP Tc minus Tb. And so you end up with an efficiency after going through the same computations of 1 minus 1 over gamma times Td minus Ta over Tc minus Tb. So you can compare this result to the result that we had for the standard Otto cycle, which is this one. And you'll see that the part that makes it less than 100% efficient, less than 1, this part, it shows up in both efficiency equations. However, for the diesel cycle, it's protected by this coefficient of 1 over gamma. Now, gamma is a number greater than 1, and so 1 over gamma is going to be a number smaller than 1. So by multiplying this ratio of temperatures, ratio of difference of temperatures, by a number smaller than 1, you're increasing the efficiency over the same sort of thing for an Otto cycle. And so, i.e., this 1 over gamma improves the efficiency. So this is just to say that in general, diesel cycles can be more efficient than Otto cycles. Also, on top of this, you can get higher compression ratios for diesel cycles because the air is compressed without the fuel present. So, that means that you don't have to worry about the air-gas mixture exploding by compressing it too quickly, or by compressing it too much. So you can compress the air as much as you want, then add the gas and light it, and so you can get better compression ratios, and you have this 1 over gamma efficiency factor that helps. So generally, diesel cycles will be more efficient. The only downside is that they're generally slower, and so you have less power output. So or rather, you have not necessarily, yeah, you have less power output, but you can have a lot of torque. So that's why these will often be used in like very large trucks. And like tractors and so on, because you need a lot of torque, but you don't necessarily need a lot of power. So, and the extra efficiency is just nice. When is it like most efficient? Yeah. So efficiency is a fraction. It's a fraction of the amount of heat that enters. It's the fraction of the amount of work done divided by the amount of heat that was required to do that work. So it'll always be between 0 and 1. 0 means that you produced no work even though you input some amount of heat, and 1 means that all of the heat that you input turned into work. So efficiency, a higher efficiency is a good thing because it means that you're using less of that heat, or you're losing less of that heat to waste, basically. Now, while both the diesel and the Otto cycle are, at least can be idealized as quasi-static, in general in the real world, neither the Otto cycle nor the diesel cycle are irreversible. And one way to see that is the reservoirs, the temperature reservoirs are at different temperatures from the gases within the engine. So let me explain. So one way that you can make an irreversible process is by just taking something hot and putting it next to something cold. Because the heat will flow from the hot thing to the cold thing, and you can't really make it go backwards without expending extra energy. So that would be an example of an irreversible process, and that results because the rate at which the heat flows is non-infinitesimal. In order to have heat flowing between two things of different temperatures, you need to have an infinitesimal temperature difference. But that can't happen here. The air outside that you bring in is just the temperature it is. And so, for example, in the Otto cycle, when you're effectively cooling down your air by expelling your exhaust and bringing in more gas from the outside, well, you can't work that backwards. this would be effectively like putting an ice cube inside your piston. It would cool down the gas, but you couldn't reverse that process because there is a temperature differential. Whereas if instead you somehow had the only time heat flowed was when there was zero or minimal temperature differential, then you could potentially have a reversible process. And we know that in general, reversible processes will be more efficient. There's a reason why irreversible processes are irreversible, and it's because something's lost that can't be regained without expending extra energy. But it turns out that we actually can make a reversible cycle in a real engine. However, in order to do so, it requires that the only time heat flows in, that it flows in from a place that has nearly the same temperature. Like if you have your gas is at 350 Kelvin, then the temperature that of the reservoir that it's getting the heat from should be 350.0001 Kelvin or something like that. Now, obviously, that will still technically be irreversible, but it'll be a lot closer to being reversible than the case where you have large temperature differences. So in order to do that, we can't have heat flowing in during processes where the temperature changes, because if the temperature changes, then at some point during the process, the heat will be, or the temperature differential will be non-infinitesimal. So the end result is that we can only have heat flows when the temperature is constant. I.e., we can't have heat flowing in during isobaric or isochoric processes like in the Otto or diesel cycle. We have to have heat flowing only during constant temperature processes, i.e. isothermal. So instead of having isobaric and isochoric processes in our Otto cycle or diesel cycle, and then also having the adiabatic ones, we need to replace those isobaric and isochoric processes with isotherms. So this thing where we take a cycle and we just replace the isobaric and isothermic isobaric and isochoric processes with isothermic processes, this produces something that's called the Carnot Cycle, named after a French fellow, I presume, because you don't pronounce the T at the end of the word or at the end of the name. And so the Carnot cycle is an example of a cycle where you can add the heat quasi-statically or reversibly. Well, let me write quasi-statically. And this is because the engine is held at a fixed temperature when we need to add the heat. The temperature just isn't changing while heat is being added. So let me draw the diagram here. So let's say that you start off, it doesn't matter where we start off, let's put A here. So we're going to have an isotherm to B. Then we're going to have an adiabat. Oops. To C. So I'm going to say that this is an isotherm. This is an adiabat. Then we have another isotherm to D. And then we have an adiabat back up to A. Now this relies on the fact that adiabatic processes are always steeper in the PV diagram than isothermal processes. If that weren't the case, then you'd be kind of out of luck because you wouldn't be able to kind of close up your loop. Now, so because these are isothermal processes, we can just define their temperature. So let's say that the temperature here at this isothermal process is TH, and the temperature for this isothermal process is TC. We know that adiabatic processes don't have any heat flowing in or out of them, right? So the only way that we can have heat flowing into or out of the system, which we need in order to have a process occur at all, is during the isotherms. So where is the heat flowing in? Well, the heat is going to flow in at the higher temperature and it's going to flow out at the lower temperature. So here we have heat flowing in into our system along the top isotherm. So this would be QH. And then heat flows out along the bottom isotherm, QC. So this would be an example of a process of an engine that could be in principle built in real life. This could be done, this could be made reversible, or at least quasi-static, like easily quasi-static. So what's the efficiency? Well, we know that the efficiency is 1 minus the absolute value of QC over QH. So we need to compute those things. Now we know that QC and QH are going to be the heat added during the process that goes from A to B or C to D. So let's compute. So when the gas goes from A to B, we know that because it's an isothermal process, the internal energy isn't changing, which tells us that the magnitude of the heat that enters or leaves the system, in this case for A to B, it's heat entering the system, this should be equal to the work done during that process, the work that's output during that part of the process. This is not all of the work done by the cycle, it's just the work for that isotherm. But we know how to compute the work for an isotherm. I'm not gonna rederive it again, I'm just gonna use the formula. It is nRTH in this case, because that's the hot temperature, times the log of VB over VA. Okay, and similarly, from C to D, again, the internal energy doesn't change. So we have that the magnitude of the heat that leaves the system, this should be equal to the negative of the work that enters the system. This is just so we can make sure, because in this case, the work is negative, so we need to stick a negative sign in front of it to make it positive, so it matches the absolute value. And the negative of the work done would be negative nRTC times the log of VD over VC. And then we can absorb that negative sign into the logarithm by flipping it. So this would be nRTC times the logarithm of VC over VD. So plugging this in, plugging both of those QHs and QCs in, come on, scroll please. We find that the efficiency is 1 minus TC over TH times the log of VC over VD divided by the log of VB over VA. But now, again, we can use the fact that BC, the process that goes from B to C, and the process that goes from D to A, those are both adiabats, so we can simplify even further. We know that T times V to the gamma minus 1 is a constant, just like before. And so we have that TH, this is the temperature, this is the hot part of the temperature, this is at B, should be related to TC by this relationship. So TH times VB to the gamma minus 1 should be equal to TC times VC to the gamma minus 1. Instead of having TB here, I put TH because we already know the temperature at state B. It's the same temperature that it was the whole time during that isotherm. And similarly, we have that TC times VD to the gamma minus 1 is TH times VA to the gamma minus 1. So putting these together, we have that VB over VA is equal to VC over VD. Just rearrange this and then divide one equation by the other. And so the end result is that the log of VC over VD divided by the log of VB over VA is just equal to 1. It's a result of it being an adiabat. So plugging that in to our efficiency gives us that, or our efficiency is 1 minus the ratio of the temperatures of the two reservoirs. And so what we find is that if the temperature difference is big, if your cold reservoir is very, very cold, by the way, these have to be absolute value or absolute temperature units, not, you can't be using Celsius here. So if your cold temperature is very, very close to absolute 0 and your hot temperature is very, very close to, or is just very, very large, then you can get very high efficiencies. And these processes can work in real life. It's just the more reversible you want your process to be, the slower the process will be. Because the isotherms require that you transfer heat between something that's slightly higher in temperature to your gas, or slightly lower in from your gas to a slightly lower in temperature region. So in order for this to be exactly reversible, the heat reservoir that takes care of your top isotherm has to be infinitesimally higher in temperature than the gas. Similarly, the cold reservoir, or the heat reservoir that takes care of the cold isotherm, has to be infinitesimally lower in temperature than the gas during this part of your phase. And so the smaller the temperature difference between your reservoir and your gas, the slower the heat flow. So if you want fast heat flow, you have to have a larger temperature difference. And that means that you'll have to be more irreversible. So Carnot cycles are something that could in principle be made, but they would take an infinite amount of time to run because the temperature difference has to be infinitesimal, which would mean it would take an infinite amount of time to transfer that energy. But you can make Carnot cycles in real life with just small temperature differences rather than infinitesimal ones, and you still get a fairly efficient engine. And depending on how big those temperature differences are, you can get like 90–95% efficiency, depending on, well, yeah, I mean, it depends on your temperature differences or the temperatures of your reservoirs. So, you know, like this does work and you can get very high efficiency. It's just the higher the efficiency, the slower they run and thus the lower the power output, which, you know, makes them slightly less useful for actual work, which is why we use things like the internal combustion engine and the diesel engine. So those are three standard examples that are taught in thermodynamics. And we could keep going and we could just slap together a whole bunch of different things and see what they work out to be. But at this point, you guys probably have the tools to work this out. Just slap together any cyclic combination of the 4 processes that you can make, and you can figure out what the efficiency is. Now, you might need to use different tools like the adiabatic relationship, or you might need to use the constant temperature relationship or whatever, but it's doable, right? Now, the last thing to talk about as far as cycles go are refrigerators. So I used to have a whole thing about refrigerators, but I'm not going to talk too long about it. The only point that I wanted to get at is that all of the engines, all of the cycles that we've talked about, they run clockwise in the PV diagram. And so, right, like these are all clockwise. The cycles all go like this. And so you could reasonably ask, what happens if you turn them in reverse? Well, kind of exactly what you'd expect. So think back to the diagram that I drew for an engine. You had a hot reservoir, temperature TH, a cold reservoir, temperature TC. And then we had heat flowing in, work going out, and then heat flowing to the cold reservoir. But if we run this in reverse, just reverse all the arrows. So you'd have work coming in, heat flowing into the hot reservoir from the cold reservoir. And then you just have a cycle. It goes like this. You have work flowing in, that forces heat to flow in, and then that pulls heat from the cold reservoir. Now, we know that this is a cycle. So the change in total internal energy is 0, which means that the work in should be equal to the amount of heat that leaves the system. Now, this is the amount of heat that leaves our working gas, right? So we know that the amount of heat that leaves the working gas, that's just the difference between these two heats. This would be QH minus QC, right? Just like for an engine, this is the same relationship because it's just in reverse. The only difference is that efficiency means something different here. Because our goal is to decrease the temperature of TC. It's to pull as much heat out of TC as possible. And so if we want to define the efficiency, we don't just want to define it in the same way, because we're inputting work into the system and we're trying to move heat around. So we define the efficiency as the coefficient, as we use the letter K for it, and it is the coefficient of performance. So, and the reason for this is because the reason why we use a different notion of efficiency is because otherwise, because we could get this kind of efficiency of greater than 1. So K is equal to the amount of heat that's removed from the cold reservoir divided by the amount of work that you have to put in. Now, why would we write it this way? Well, think about it this way. The way that you remove heat, heat doesn't flow from cold to hot on its own. In order to make that happen, you have to do work. You have to input energy. And that input energy is this work that you do. You expand and you apply forces to gases, you expand and compress them and so on. And so what we really care about, we don't care about how much energy escapes to the environment. This hot, this is the inside of the refrigerator. This is the outside. We don't care how much energy goes outside. All we care about is how much energy do we have to put in order to remove a certain amount of heat from the inside of our refrigerator, right? And so we just divide these two. So say we have to input 2 joules of work for every 1 joule of heat we remove from the inside of the refrigerator. Well, then you'd have a coefficient of performance of 1/2. But depending on the cycle that you use and depending on how well you engineer things, which can get complicated, you can actually get efficiencies or coefficients of performance that are greater than 1, i.e. you input 1 joule into the system, and that allows you to move 3 joules from the cold system to the hot system. For example, heat pipes have very, very high coefficients of performance because they kind of just work on their own, or at least they nearly do. So all a refrigerator is just an engine in reverse. Now, we're not necessarily just going to take a diesel cycle and start moving the pistons on ourselves and then expecting that the inside of, or the gas inside the piston is going to cool down. That's not how that works, because the real world engineering situation is a little bit more complicated, but the cycle can still be run in reverse. You just need to design a system that does that. Like, for example, you can't uncombust the gasoline, so you can't actually just run that exact cycle in reverse, but you could come up with a system that effectively does the same thing. And that's what actually is done in refrigerators, and that's why there are compressors in refrigerators and so on. So K greater than 1 makes sense because we're not stealing energy. We're not gaining. It's not like we're getting energy for free. All K greater than 1 implies is that you're putting in less work than the work that you're transferring. So the work that you input into the system, it's not actually doing anything. All it's doing is kind of coaxing or guiding energy from the cold environment to the hot environment. But all of that energy is still going to the hot environment. So really, the energy that's wasted is the amount of energy that goes, the energy that's wasted is all of the work is wasted, and all of the work, and the difference between the, and all of the energy that goes from the cold environment to the hot environment is wasted. None of that is retrievable, but the end result is, after all of this energy waste, is we get something that's colder. So it's not like you're getting energy for free anywhere. There's no energy coming in. All this just means is that you're able to push more energy, is that you're able to use a little bit of work to move a lot of heat. And there's no energy conservation breaking there, because the work isn't the thing that you're moving. The work is just allowing you to move the heat. Hopefully that makes sense. So I mentioned a while ago, Monday, that for any cycle, and maybe actually, did I mention this? I may not have mentioned this. It turns out to be the case that anytime you have no, I definitely talked about this on Monday. Anytime you have an engine, you have to have a hot reservoir and a cold reservoir. You have a place that the heat flows in from, and you have a place that the heat flows out to. And you could try to come up with some sort of cycle that doesn't have a cold reservoir, but you wouldn't be able to draw one, a PV diagram that just doesn't require heat flowing out to a cold reservoir. It just doesn't, like no such thing exists. And that is, in a sense, that is a qualitative statement of the second law of thermodynamics. That is a way that we can do it, that you can describe it. But we're going to talk about the second law of thermodynamics in a more quantitative way. So we have a lot of building to do before we can actually write down a mathematical description of the second law of thermodynamics. So with that said, with that lovely segue, let's start talking about the second law of thermodynamics. It'll take us a little bit to get there, but we will get there by the end of today, I think. So we already know that thermodynamics is more than just state variables in the first law, right? Like, I mean, first of all, you guys know that there's more than just one law of thermodynamics. So obviously there's more to it than that. And we also know that this has to be the case because not all processes are reversible and quasi-static, right? So there has to be a way to describe these things, even if they're not quasi-static. Like, this should be describable. So, for example, you might ask, well, if every system was just described by state variables of that system and the first law of thermodynamics, which is just energy conservation, there's nothing wrong per se, according to the first law of according to those aspects of thermodynamics that say this pen, which is just sitting on my hand, couldn't just suddenly jump in the air and then cool down a lot, right? Because we know that if it jumps in the air, its potential energy is going to increase. And so that energy has to come from somewhere. But according to the first law of thermodynamics, that energy could just come from, say, the temperature. The energy could come from the temperature of the system. It could come from the internal energy of the system, i.e. suddenly that internal energy could just have work done on it, which lowers its internal energy, or the molecules in the pen could spontaneously lower their internal energy, and in doing so, output that energy as work to lift the pen up. In principle, according to the first law of thermodynamics, that could happen. It doesn't violate the first law of thermodynamics for that to happen. So the question is why doesn't that happen? Because we know it doesn't. That doesn't happen in real life. If you drop an egg, eggs break significantly more often than eggs unbreak. So we need to be able to explain why that happens. And it turns out that this phenomenon, while it might not seem like it, is actually related to engines. And this goes back to what I was just saying. You can't draw a cycle with heat only coming in and work exiting, i.e. you always need some heat leaving, and so you always need a cold reservoir. And like I said, that is an example of the second law of thermodynamics. Now, before we can proceed and explain why this sort of thing happens, or why this sort of thing doesn't happen, I need to give you a few definitions. So one definition is the extensive variable. So an extensive variable is a state variable that changes with the size of the system. So examples of this would be the number of particles, the volume, the internal energy, the number of moles, etc. Those are all state variables that change with the size of the system, i.e. if you hold everything else fixed, like if you keep the temperature, the pressure, the volume, and all of those things fixed, but you if you keep the temperature, the pressure, and all of that, okay. Maybe I should just say obviously that, like, if you make your system bigger, there's going to be more particles in it. Similarly, if you make and when I say bigger, I don't just mean physically larger. I mean, like, talk about a bigger system. Similarly, you can make the volume of your gas larger, and it will change in the same way. Like the volume of if the volume of the box gets bigger, then the volume of the gas gets bigger. And if you have more particles, or if your system encloses more things, then you have more internal energy, and so on. Then there's intensive variables. Oh, perhaps another way to see this is that extensive variables are just variables that are kind of like a sum of a bunch of different properties. And so the more of the things that you have that you're measuring, the larger that thing is. So the volume would be like the sum of the volume of all of the little gas particles. And the number of particles is just the sum of the number of particles. The energy is just the sum of all of the energies of all of the particles. So as your system size gets bigger, all of those things get bigger. Whereas intensive variables are state variables that are kind of averages, or state variables that don't. State variable that doesn't. So a state variable that is kind of composed of an average, these are things like pressure and temperature. Pressure is an average of the amount of force that's being applied to the walls. So the pressure isn't going to increase if you make your box bigger, holding if you're talking about a larger system, the pressure isn't necessarily going to double. Like if your system doubles in size, your pressure doesn't necessarily double in size. Similarly, if you double the size of your system, your temperature doesn't necessarily double, because these are average things. These are things like average temp or average kinetic energy per particle, or average force applied to the wall per particle. So averages, the variables that describe like an average of some quantity over all of the particles, those would be intensive variables, and extensive variables are the ones that are just sums of a whole bunch of different things. So it turns out that every state variable is either extensive or not extensive, i.e. intensive. And you can check that mathematically. Like you can verify that, say, if the number of particles goes up, then you can see that the and everything else is held fixed, then you'd find that the temperature goes up, or sorry, not the temperature, the internal energy goes up, i.e. if one of these goes up and the intensive variables are held fixed, then the other ones will go up. However, if these are changed, but the temperature is held fixed, then the pressure won't change, right? So you can verify mathematically how these things change in relation to one another and in relation to changing the size. So if we want to describe the second law of thermodynamics mathematically, we should think about how we describe the first law of thermodynamics. So the way that we did that was we noted that, well, there should be some sort of energy conservation. Energy conservation was what we were trying to capture with the first law of thermodynamics. But at that point, we didn't have a notion of the internal energy of the system. So we had to add a new state variable that captured that so we could write an equation. And so that equation was delta U equals Q minus W. So we need a new state variable to mathematically capture the second law of thermodynamics. So let's try to come up with one. Now, we know that this is going to be related to heat, because we know that a formulation of the second law of thermodynamics is that there's always heat lost in an engine. So just like how the law of conservation of energy, or how the first law of thermodynamics was a statement about conservation of energy. So we needed some sort of energy, or we needed an equation that tells us about energy. We know that the second law of thermodynamics should involve something that tells us about heat. So we're going to build towards this, but I'm going to try to do this in a way that seems consistent. So we needed that new state variable, and we need one that involves heat. Now, we already know that the first law of thermodynamics involves heat, but that's not going to help us because that's the first law, not the second law. What we don't know is we don't really have a formula for heat in the same way that we have a formula for work. So recall that work arises quasi-statically from many infinitesimal steps. Many infinitesimal, I'm gonna run out of space, steps of dW equals P dV, i.e. you can compute just a teensy tiny bit of work and make that done quasi-statically by doing very infinitesimal steps of taking the pressure and then increasing the volume a little bit, and then taking the pressure and then increasing the volume, and then fixing the pressure and then increasing the volume a little bit, fixing the pressure, increasing the volume a little bit. That will do little bits of work bit by bit, and it'll do it quasi-statically. But the thing is for the second law of thermodynamics, we need something relating to heat, and we don't yet have an equation that looks like this for heat. It turns out that we just haven't written it down yet. Heat does indeed have such an equation. Now, we want something like the following. We want dq is equal to something times d something. That's what, like, heat and work really should be on equal footing, so there should be some sort of equation. Now, we can figure out what fits into those parentheses by comparing it with work. So we know that work is done by a gas or on a gas because of pressure, i.e. if there's a lot of pressure in a gas and then there's a piston, it's because of the pressure that the piston goes up, and that so pressure drives work. So if we want to match our formula for dq with the formula for dw, the thing that should go into the first parenthesis should be the thing that drives heat flow. So what drives heat flow? Well, I don't know why I erased the whole thing. What drives heat flow is a temperature difference. So we should have T as our first, or filling in our first parenthesis. It's the thing that drives heat flow, just like how P drives work. Now, the question then is, what do we put in here? Well, we're kind of out of luck, right? We know that work is P and V. So what would Q be? Q is T and what? Well, we don't really have another state variable that we can use. T du wouldn't really make sense because we know that you don't increase the internal energy a little bit, holding the temperature fixed in order to add heat to the system. That's not how heat is done. So we're kind of stuck. So I'm going to call this a new symbol. I'm going to call it S. This is our new state variable that we need. So the question then is, what is S? Well, from this formula, we know that it has units of, well, we know the units of dq are in joules. We know the units of temperature is in Kelvin. So the units of S should be in joules per Kelvin. So it certainly can't be internal energy because internal energy has units of joules. So what state variable is this? Well, it's no state variable that we've encountered yet. There are no state variables that we've encountered yet that have units of joules per Kelvin. Now, just as a quick note, temperature and pressure are intensive variables. And so it makes sense that there's a correspondence here. Now, volume is an extensive variable. So you might also infer that S, whatever it is extensive, just like volume, so that they're kind of matching each other, so that they're analogous. And so we're going to try to come up with a state variable. And by the way, this is just something that we're doing, like we're constructing this from scratch. There is some state variable that we just haven't thought of yet that's extensive and has these units and tells us how heat transfers. Now we just need to describe that thing and think about it. Now we're going to give it a name. Our new state variable new extensive state variable is S, and we call it entropy. So we haven't talked about what entropy is yet. It's just a word. It's just a name. Now we need to explain it. So let me back up. I don't want you to think, oh, S happens to be entropy. Entropy is this thing, and then we just stumbled upon this result that entropy is the thing that does TDS. No, it's not that way. Think of entropy as just a name. Like if you haven't heard the word entropy, then you're in luck. If you've heard of it and you have some like precognition? No, that's not the right word. Preconception. If you have this preconception about what entropy is, throw it out because this is just a name. We could have called it Zilbosler or something. Like we could have just called it anything. This is just a name for this thing S that we're making up. Now, if it's true that Q can be written this way, then just like work, we could write what the total heat is during a process. Total heat transfer is. Q would be an integral from A to B of T ds, just like how work is an integral from A to B of P dV. Now, we haven't done this before, but we can turn these equations around. We can turn them around so that instead of writing Q in terms of changes of state variables, we can write changes in state variables in terms of W and Q. So for work, we have dW equals P dV. And so that would imply that dV is equal to work, or is equal to dW divided by P, which would imply that the change in volume of a gas which is VB minus VA, is an integral from state A to state B of a small amount of work divided by the pressure. So you add a little bit of work, you divide the amount of work done by the pressure that you did, and then you do it again, and you keep doing it again. You add up all of those works divided by pressures, and then that will give you a change in volume. We don't happen to use this equation very much because it's actually really easy to measure changes in volume. It's harder to measure amounts of work done. So this formulation isn't particularly useful because we just don't measure, we don't measure work directly, we do measure volume directly. So the reversed one, the one that looks like this, is more useful. However, for heat, it's a different story. So heat can be written as TdS. And so that means ds can be written as dq over T. And so we can actually write the change in the variable S, the change in entropy, which is SB minus SA, is equal to an integral from A to B of dq over T. And now this equation is useful because up until now, we didn't even know what S was. So at least this gives us a way of measuring how the state variable changes, and we can fairly easily measure the amount of heat that we add. In particular, for different processes, we know how much heat we add. For example, for an isobaric process, the amount of heat that you have to add in order to get, if you add a small amount of heat dq, then the amount of temperature change that you get is NCP dt. So you can write dq in terms of a constant times dt, and then you can actually just do that integral and compute the change in entropy. So this formula is useful, unlike the formula for volume, and that's just because entropy is hard to measure directly, whereas volume is easy to measure directly. So let's ask the question then. Let's just kind of get our feet a little bit wet and work a quick example. So if gas undergoes adiabatic expansion, what is the change in entropy for that process? What is delta S? Well, right out the gate, we have a formula for delta S. It relates to the small amounts of heat added divided by the temperature. It's an integral. But we know that for an adiabatic expansion, there is no heat added or leaving the system. So dq is 0 for an adiabat, which implies that delta S is 0. So now we can finally finish our four special processes. We had isobaric, isochoric, isothermal, and then we had adiabatic. But now we have another word for an adiabatic process. We can define an isentropic process. This is a process where one of the state variables, in this case S, doesn't change. Just like how for an isothermal process, it's where delta T is 0, or for an isobaric process, it's where delta P is 0. An isentropic process is an adiabatic process. It's just another name. So that completes our story of the four thermal processes. They're just the four state variables, or four of the state variables, when each one is held constant. It tells you what kind of process happens. Now, we know that there is an equation of state relating the pressure to the number of molecules, the temperature, or the number of moles, the temperature, and the volume. This is PV equals nRT. It's the standard ideal gas law. We also know that there's an equation of state for the total internal energy of the system. Is this like a rectangle and a square type of deal? What? Deal? What do you mean a rectangle and a square? Oh, no. All isentropic processes are adiabatic, and all adiabatic processes are isentropic. They're just synonyms. Right. It's just we hadn't introduced the notion of entropy, so calling it an isentropic process wouldn't have made sense yet. So like I was saying, we have equations of state. We have an equation that tells us how P, V, N, and T relate to each other. That's the ideal gas law. We also have an equation of state telling us how the internal energy, U, and the number of moles and the temperature, N and T, relate to each other. That's another equation of state. Now, we don't yet have an equation of state for the entropy. The entropy is a state variable, so we should be able to describe it in terms of the other state variables using an equation of state. Now, it turns out, I'm just going to tell you what the formula is, the entropy for an ideal gas is the following. And I'm not going to give you the details as to how this was derived. It's S is a function of the number of particles, the internal energy, and the volume is N times KB, this is the Boltzmann constant, times the logarithm of V over N times U over N to the 1 divided by gamma minus 1. It's a terrible formula, I know. So you can do a lot with this. Like you can just compute the entropy of two different states and then find the difference, and you could figure out what the change in entropy is for those two states, just in the same way that you can find the change in sorry, just in the same way that you can find the change in internal energy by just finding, you calculate the internal energy of one using NCVT, you find the internal energy of the other using NCVT, and then just take the difference. The only thing that makes this particular equation stand out, oh, we are going to finish early, super early, that's okay. The only thing that makes this equation stand out is that unlike the other equations of states that we've talked about, this equation of state depends on the type of gas. So the entropy of a diatomic gas is going to be different from a monoatomic gas, even if you have the same internal energy, the same number of particles, the same volume, etc. All of those things being the same, the entropy is still different because the type of gas is different. That's what this gamma tells us. So this is a little bit unusual, but perhaps it's not, because, well, we haven't actually talked about what entropy is yet, so we can talk about that. And I probably just wax poetic about that in a little bit at the end of the lecture, just to eat up time. So we can just do a lot with this formula, and in fact, we can actually use this to find the entropy for special processes, or the change in entropy. For other three special processes. So for an isochoric process, you can just plug in the values using the ideal gas law, the fact that the volume is constant, and so on. We find that delta S, which is an integral from B to A, dq over T. Well, we know what dq is for an isochoric process. It's an integral from A to B of NCV dt over T. This is just equal to NCV times the log of the temperature, of the ratio of temperatures. For an isobaric process, it's the same thing, but we just have Cp instead of Cv. So we have delta S is equal to NCp times the log of the ratio of temperatures. For an isothermal process, it's a little bit different. We have that delta S, it's again an integral from A to B of dq over T. And this is just equal to 1 over T times the integral of dq, because for an isothermal process, temperature is constant, so we can pull it out of the integral. But this is just 1 over T times the total amount of work, or the total amount of heat going from state A to state B. But for an isothermal process, the work and the heat are equal because the change in internal energy is 0. So this is just the work done from A to B divided by the temperature, which is just, and we already know the work done by an isothermal process, we've calculated that. It's nR log of VB over VA. That is the change in entropy for an isothermal process. Now, I just want to make it super clear, in case it wasn't, I actually don't think I even mentioned this. Just like how the work done is only equal to P dV when the work is done reversibly, the heat, that is the heat transfer dq, is only equal to T ds when the heat energy, or when the heat is transferred reversibly, meaning when the temperature differential is infinitesimal. So that's a useful thing to know, because we're going to find a lot of cases where the heat transfer is not reversible. And by the way, I mentioned this because it's really easy to make a reversible, to make work done reversibly. Work is easy to reverse, right? Because as long as the piston on your gas is moving at a fixed rate, it's completely reversible because it's not accelerating. However, The moment you have a non-infinitesimal temperature differential that's causing a heat transfer, now you have an irreversible process. And so the heat is just not governed by TdS anymore. Or rather, in a sense it is, but you can't treat them as infinitesimals anymore. So before I talk a little bit more about that, I want to talk about one other thing that that explains why entropy is useful, and that's TS diagrams. So we've talked about PV diagrams. We know that P and V are related to work, so a PV diagram is nice because you can find the area under the curve to find the amount of work done. So because we have a new state variable now, we can draw new diagrams. We can plot T against S, And then you can, and again, this is just, you just have states, state variables. At each state, you'd have some value of entropy and some temperature. And then you can find that the heat that flows into or out of the system from A to B is just an integral of dq. But that is just, by definition, an integral from SA to SB of T ds. It's just the area under the curve. So the area under the curve in a TS diagram is the heat that's added to the system. And if you go from left to right, it's heat added to the system. If you go from right to left, it's heat leaving the system. So that's kind of nice because now there's kind of like a duality, right? You have PV diagrams, which are useful for work, and you have TS diagrams, which are useful for heat, and you can use both. Like we know how they relate to each other. So you can relate one to the other. So you could just compute the work in a PV diagram and then do the same process in a TS diagram and then compute the heat. And it actually turns out that the Carnot cycle in particular is particularly nice in a TS diagram. Now let's think about what the Carnot cycle is. The Carnot cycle is a cycle where you have isothermal expansion, isothermal contraction, adiabatic expansion, and adiabatic contraction. So let's say you start at the top left, and then you isothermally add heat. Well, this is a TS diagram. So isothermal means that heat's coming in, and the temperature is staying constant. So if the temperature is staying constant, then that means that you're going from left to right. You're adding energy to the system. Looking at our formula here, if U increases, then the entropy increases. So you're moving to the right on your diagram, but your temperature is constant. This would be an isotherm on a TS diagram. From B to C, if you look back in your notes, you'll see that B to C was an adiabat, meaning that no heat enters or leaves the system. Now, an adiabat, as we already discussed, is just another word for an isentropic process, a process where the entropy is fixed. So that's A, that's B. So from B to C, we just go straight down. This would be isentropic or an adiabat. And you can probably see where this is going. When we then do our isothermal compression, we have an isotherm that's again a straight line because it's at constant temperature, and then we do our adiabatic expansion, which is again a straight line. And so in the TS diagram, the Carnot cycle is just a rectangle. So the heat that's input to the Carnot cycle is just the temperature difference times the entropy difference of the two parts of the cycle. And then because it's a cycle, the work done is just equal to that same thing because the internal energy is unchanged. So hopefully, if nothing else, at least this use of TS diagrams justifies why we might care about entropy, because it means that you can depict otherwise complicated processes in a new light that makes them a lot simpler. So, but that's not the only reason we care about entropy. Like, clearly, you guys have all heard of the word entropy, I hope. And it's used in a lot of like this, what's the word? The notion of entropy shows up a lot in like pop science. So let's try to get into some So let's get into the weeds, as it were, about what entropy is. And in order to do so, it's the transition from high potential energy organized states into low potential energy. So it doesn't necessarily have to do with potential energy at all. Yeah, it doesn't have anything. It doesn't necessarily have anything to do with potential energy. It's related to disorder, but it's not necessarily a measure of disorder. There are disorderly states that have lower entropy than ordered states. Such things exist. But anyway, I'm going to get into the details. So in order to talk about what entropy is and why we might care about it, let's consider multiple systems and how they interact with one another. So we're going to consider two systems that are in thermal contact with each other and only each other, meaning that they're insulated from the environment, but they're in thermal contact with each other. So we have our thick walls to indicate that it's insulated from the environment. Oops. And then they're just a thin wall connecting them. So you have a gas in box A, a gas in box B. Say this is at temperature A. This is at temperature B. And let's say that temperature A is bigger than temperature B. So we know that because gas A is at a higher temperature than gas B, we know that heat is going to flow through the wall. The temperature of gas A is going to decrease and the temperature of gas B will increase until they come to equilibrium. So the heat leaving A is equal to the heat entering B. Right? That's just energy conservation because the system is isolated. Now, so long as this is done quasi-statically, if, say, TA is equal to TB plus a very, very itty-bitty temperature difference, an infinitesimal temperature difference, then we can write that ds1 plus ds2, these are the changes in entropy for the two systems, should be equal to 0 because it's extensive. Another way to see this, by the way, is the following. So we would know that dq1 should be equal to t1 ds1, and dq2 is equal to t2 ds2. Now, we know that the heat that enters one leaves the other. So we also know that the absolute value of dq1 should be equal to the absolute value of dq2, which implies just that dq2 is equal to negative dq1. Okay, so we can actually relate the changes in entropy. So ds1 should be equal to dq1 divided by t1 plus dt, right? We're assuming that there's an infinitesimal temperature difference, and ds2 is equal to dq2 divided by, sorry, oh no, I should be using A's and B's, my bad. A, B, A, B, B, A, B, B, A, B, T, sorry about this, B, B, B. Okay. So, right, okay, so the fact that, so now, oh, this should be DSB. So we have DSA plus DSB. This should be equal to, well, dQA is negative dQB. So this is equal to dQB times 1 over TB minus 1 over TB plus dt. Now this seems like it looks really terrible, but you can actually just write this out, and you'd find that This goes as dqb times dt. And so so basically you could do an expansion in dt. If you like treat dt as a variable x and then expand around x equals 0, do a Taylor series expansion. And the point is that if dt is infinitesimal and dq is infinitesimal, then the end result is the product of two infinitesimal things. Sorry, which means that the difference is basically 0. Like this is something that we do in calculus a lot, where if you have you can treat dx as not 0, but then if you have dx all squared, then that's 0, because if you have something infinitesimal, you multiply by another thing that's infinitesimal, that's even more small, that's even smaller. So the point is if the process is infinitesimal, or if the process is done reversibly, i.e. infinitesimally, then what we find is that the sum of the entropies, the sum of the changes in the entropies is 0. That's what we found here. And in the infinitesimal limit, it just is equal to 0 rather than being approximately 0. Now, however, for an irreversible process, we have that QA is equal to TA delta SA, and QB, well, it's roughly equal to it anyway. And QB is roughly equal to TB delta SB. And so we can do the same thing again. Now let's look at how the changes in entropy compare. So delta SB would be roughly equal to QA over TA, and delta SA, sorry, QB over delta S over delta TB. Delta SA would be roughly equal to QB, not QB, QA over delta TA, not delta T, just T, TB and TA, I'm sorry. So this is all to say, well, we know that the heat that comes from one goes to the other. So because QA plus QB should be equal to 0, we have to have that the changes in entropy are different. Entropy is, so much of this, yes, much of this is fair game. It is highlighted in yellow. So let's think about what SB and SA are. Did I write this in the right order? Yeah. Okay, so if they have the same Q, right, same magnitude anyway, then the one with the higher temperature will be the one that decreases its, or that changes its entropy the least. So because A is at a higher temperature than B, Q over TA will be smaller in magnitude than Q over TB. So we find that the magnitude of the change in entropy of SA is less than the magnitude of the change in entropy of S, or than the magnitude of the change in entropy of B. And so the end result is, one of these is negative, by the way. Delta SA is negative because you have heat leaving the system, and delta SB is positive because you have heat entering the system. So the end result, this one is positive, this one is negative. The end result is that the sum of the changes in entropy of the whole thing, delta SA plus delta SB, well, this is a bigger negative number than this one is small. So this whole thing is greater than 0. This would be like, you have like 5 here and you have like -4, right? So you would still end up with something greater than 0. So in this example, we had an extensive process, or sorry, we had an extensive variable, and we may have thought that if the process was reversible, the sum, or that variable will just be the sum of that variable for the two separate systems. And that's true. We found that the change in entropy is 0. Sorry, that the total entropy is just the sum of the changes in the total entropy of the system is just the entropy of the initial systems, because the change in entropy is 0. And so we found that indeed entropy is an extensive variable, because if you just combine two systems, the total entropy you have is just the sum of the entropies that you had. However, for an irreversible process, if you combine two systems, it actually turns out that the entropy isn't just the sum of the two entropies, it's greater than that. The entropy of the system increases when you combine two systems in an irreversible way. And so that leads us to a conclusion that delta S of a whole system is greater than 0 for irreversible heat exchange. And we can actually generalize this statement. Let me put a box around this because that's a big deal. And this is what we just found, by the way. We had irreversible heat exchange, and we found that the change in entropy of the whole system increased because you had the sum of the entropies was smaller than the entropy of the combined thing. So the entropic version of the second law of thermodynamics, can be phrased as follows. For any process in a closed system, and closed is important, we have that, let me move this over just so that it can fit on the line. Delta S is greater than or equal to 0. This is the standard way of writing the second law of thermodynamics. There are other ways to do it. But the point is if you have a process that's occurring in an isolated environment, meaning there's no energy entering or leaving the system, regardless of the type of process, whether it's reversible, irreversible, quasi-static, not quasi-static, whatever, the entropy of the system will either stay the same or increase. Now, for reversible processes, the entropy will increase. Sorry, the entropy will stay the same, as we saw when we talked about reversible heat flow, infinitesimal heat flow here. However, if the process is irreversible, then we end up with entropy strictly increasing. The change in entropy is positive. So just as a note, reversible processes have delta S equal to 0. So I promised that this was somehow related to engines. And the way to think about this is imagine if your engine could convert all of its heat to work. Well, work doesn't change the entropy of a system, right? The entropy of a system, like work is just work. It's not entropy. If you do work on a system, like you can use that to do whatever you want. So if you pulled heat out of your hot reservoir, the entropy of that hot reservoir would decrease because we know that heat is related to temperature times the change in entropy. So if you remove heat, then your entropy decreases. But we know that for every process in a closed system, you have to have the entropy either staying the same or increasing, which means that you have to have some of that, you have to have that heat going somewhere else that increases the entropy even more. And the only place that can go is to a cold reservoir. That's how these two formulations of the second law of thermodynamics are related. Now, we can actually use the second law of thermodynamics in a useful way. We can talk about the efficiency of an engine. So the efficiency, remember, is it's the work done divided by the magnitude of the heat flowing out of the hot reservoir. This is 1 minus the magnitude of the heat flowing into the cold reservoir divided by the heat flowing out of the hot reservoir. And we found that this was, we know that we can write the heat in terms of a change in entropy and a temperature. So this is 1 minus Tc divided by Th. This is heat flowing into and out of the hot and cold reservoir times the ratio of the changes in entropy, delta Sc divided by delta Sh. We're just saying that the entropy of the hot reservoir, the heat flowing out of the hot reservoir is equal to the temperature of the hot reservoir times the change in entropy of that reservoir. And the same thing is true for the cold reservoir. Now, for an irreversible process, we know that the total entropy is going to increase. And so that means that the change in entropy of the cold reservoir has to be more than the change in entropy of the hot reservoir, i.e. delta Sc should be greater than delta Sh. And so, but for a reversible process, we know that those should be the same. Delta Sc should be equal to delta Sh. And so, but we've already seen an example where delta SC is equal to delta SH. Or rather, we've seen an example where the efficiency is just 1 minus that. Let me write this out one more time. This would imply that the efficiency for a reversible engine is 1 minus the ratio of the temperatures of the reservoirs. But this is the efficiency of the Carnot cycle. And Carnot cycles are reversible, so it all checks out. But what this tells us is that the Carnot cycle is the theoretically most efficient, like you literally can't do better than this, it's physically impossible, most efficient engine that you can make. Because any other engine that's not irreversible, any other engine that is irreversible will have the same decrease in efficiency multiplied by a number greater than 1, right? They'll have the same TC over TH, but that will be multiplied by something bigger than 1. And the smallest that ratio can get is 1, and that's precisely that's precisely for the Carnot cycle. So from the second law of thermodynamics, we actually have proven that the Carnot cycle is like regardless of what cycle you come up with, the Carnot cycle is the most efficient, or at least it's tied for most efficient. You can't make one that's better. So that takes us through to 1130. I do want to just talk for a minute, and this part, it's not in the lecture notes, it's in the LibreText if you want to look at it, but I'm not going to hold you responsible for this part. But we haven't actually really talked about what entropy is. So there is a way of talking about entropy that puts physical meaning to it. So far, all we've really done is we've just said that there is this thing called entropy, and it has these properties, and then we can do math with it because, you know, we gave it some properties and it has those properties. But we can actually put physical meaning to it. And the way that we do that is by saying that entropy is related to the number of entropy, really it is. Entropy is related to the number of microstates that correspond to a given macrostate. Now I have to explain what that means because I haven't explained what either of those are. So a macrostate is a set of state variables, right? So like if you have a system with a certain set of state variables, those state variables specify a macrostate. It doesn't tell you where each of the particles are in the gas. It doesn't tell you how fast every particle is going. It tells you some averages, and it tells you macroscopic properties of that system. A microstate, on the other hand, is a complete characterization of the position and the speed and the orientation and all of those things of every single particle that makes up the system. So, for example, if you knew the position of, what would be a better example of this? Let's say you just had 2 molecules in a box, right? Not a very dense gas, but let's say you had 2 molecules in a box. If you knew where each of those molecules were, and you knew how fast they were going in what direction, assuming they're monoatomic, then you would 100% know the microstate. And maybe for 2 molecules in a box, you could actually pretty well know that. Quantum mechanics would get in the way a little bit, but you can at least isolate the position and momentum of most of those of those 2 particles. But for a standard type of gas that we're talking about, that we talk about in this course, these gases are composed of several moles of molecules. We're talking 10 to the 23 molecules. And so there's no way that you could possibly know all of the positions and speeds and directions and all of those things of every single one of those molecules. It's just not physically possible. So the reason we use macrostates is because they're characterizations of the conglomerate behavior of all of those particles. And because there's so many of them, we can just approximate those their motions and positions as being random. And that's a fairly good approximation, so it's safe to do. And so what entropy really is it tells us how many different microstates are there for the macrostate that we're observing. And the reason why this thing is useful is because it tells us how likely a thing is to be in that macrostate. So let's say that you have 1 trillion particles, just because. And let's say that means that you have 1 billion particles maybe, and that means that you have 1 quadrillion possible macrostates. It'd be a lot more than that, but just bear with me. Maybe you have 1 quadrillion possible macrostates. Now, some of those macrostates will be something like all of your particles are in one corner of the room. or all of your particles are moving left, or some combination of those, right? Those would be microstates. Those would be examples of fairly bizarre microstates where something very peculiar has happened. It's not a very random microstate. And then you'd have some microstates where basically the particles are just randomly distributed and they just have random speeds. That would be another microstate. The question then is, what is the most likely microstate to occur? Well, these particles are bouncing around randomly, moving off walls, whatever. And so they're going to be passing through a whole bunch of different microstates really, really quickly. Like at one instant, you'll be in one microstate, and then a fraction of a second later, when the particles have moved a little bit, you'll be in another microstate, and so on. And you'll just be moving through microstates. But we know that in the real world, if you put a gas in a box and you leave it alone for long enough, it'll just kind of stay in the same state. Its temperature won't change, its pressure won't change, its volume won't change, and so on. So how could it be that the microstates are changing so very rapidly, and they're always changing, and yet the macrostate is staying the same? Well, the key here is that most microstates correspond to a single macrostate, meaning that it doesn't matter if you have 1,000,001,000,001 particles on the left side of your room and a trillion particles on the right side of the room. That's basically the same macrostate as the reverse, 1,000,000,000,000 particles on the left side of the room and 1,000,001,000,000 particles on the right side of the room. And there's going to be a lot of phenomena like this where you have very slight changes in your microstate that lead to the same macrostate. And so what entropy does is it tells us how many microstates are there, or the entropy of a system is really a measure of how many microstates correspond to a given macrostate. And so one of the ways of seeing that that systems tend to increase their entropy is that they tend to go towards systems that have more microstates associated with them. And the reason for this is if you have a system that starts off in a really low entropy state, meaning that there's only a few microstates that correspond to it. And the typical example is like a really well-ordered system. If you have them all at if you have all of your molecules in a certain place, then you can say the position of every single one of those molecules. And there's less of those there are less of those microstates where they're all in one place than if they were allowed to spread out. So that would be a low entropy system because that microstate or those microstates would correspond to a macrostate. And there would be fewer of those microstates corresponding to that macrostate where they're all in a really tiny volume. And so, but we know that they're all randomly moving. And so at any given instant in time, the odds of them passing through a macrostate or passing through a microstate, the odds of them entering a microstate that has the same macrostate as a lot of other microstates is really high. Like while you might occasionally get into one of those macrostates that have only a few microstates, most of the time when you're bouncing around, whatever microstate you're in will correspond to basically one macrostate. It'll correspond to the macrostate where everything's uniformly distributed. And so the second law of thermodynamics, another way to view this is that it goes from macrostates with only a few microstates to macrostates with a lot of macrostates. Just the probability of ending up in macrostates with lots of microstates is much, much higher. So that's why entropy increases, just as a result of probability. The odds that a system of particles ends up in a state that macrostate that corresponds to a quadrillion different microstates, as opposed to a macrostate that corresponds to 10 microstates, it's much more likely to end up in those high macrostates. So the way that another way to view entropy is just it's a measure of how many different ways you can arrange a system without changing the macroscopic properties. And that's why people talk about entropy as if it's like disorder, because like the typical analogy is if you have a room where all of your furniture and all of your objects are arranged really, really neatly, the macrostate, i.e. like how the room looks, will change dramatically if you only move your objects just a little bit, right? Like if you tip a cup over in a room that's perfectly orderly, the observed macrostate will change dramatically, right? Like you'll notice that. But if you have like clothes everywhere and you have food everywhere and dishes on the ground and all sorts of random, like a horribly messy room, if you tip over one more glass, are you really going to notice? And so the point is that those the more disorderly state will be the state that has more of these microstates associated with it, and hence higher entropies. So that's why people often say entropy is a measure of disorder, and that the second law of thermodynamics says that things tend towards more disorder. That doesn't have to be the case. You can have states that are more orderly, but have more microstates associated with them. Think of like there are some crystals that behave this way, but that's just the general perception. Anyway, so that last bit on entropy won't be on the exam that I just talked about, just because it was kind of, what is the word? I was kind of, not winging, it's not the right word, but it was kind of more abstract. But the rest of this lecture, the lecture notes that I'm going to be posting, is fair game. So do take a look at the lecture notes. Do take a look at the LibreText as well. I'm going to end the recording here, but I will open the floor to questions.